students, this is Dr. Anita Raj, your chemistry mentor, welcoming you for another session in chemical bonding. Today we are going to see about the types of Vanderwaals forces, that are London force, Debye force and Keesom forces. Okay. So before going into the types of van der Waals forces, you should know what is a van der Waals force. Okay, actually these van der Waals forces are short-lived electrostatic forces of attraction. Okay, and of course this van der Waals force, it exists between all kinds of atoms, molecules, and ions when they are brought close to each other. Okay, actually, these van der Waals forces, they don't depend upon the valence electrons. That means they have no concern with valence electron. And also, it's possible to see these van der Waals forces in neutral molecules, in atoms, and also in ions. Okay. And of course, these inert gases, even inert gases also develop van der Waals forces. Okay. These inert gases, they develop these forces when brought close to each other. Okay. So now we shall see about the van der Waals forces, right? See, under the types of van der Waals forces, we are having three categories. That is, the first one is the dipole-dipole interactions. Okay, the other name for this type of interaction is Keesom forces. Okay, actually, what do you mean by this Keesom force or the dipole interaction? Forces which are developed due to dipole-dipole interactions are called as Keesom forces. Okay, so see, let us consider a polar molecule. Okay, it's having a minus charge as well as a plus charge. Okay. When do you call a molecule as a polar molecule? When they are having a permanent dipole moment. Okay. See, when these polar molecules, when they are brought closer, these two polar molecules, they will be orienting themselves in such a way that the positive end of one dipole will be in opposite to the negative end of another dipole. Can you understand? Thus, the two dipoles, they attract each other. Okay, they will be attracting each other, okay, by an electrostatic force of attraction. So this is electrostatic force of attraction. So thus it is possible to form a short-lived dipole-dipole interaction at low or moderate temperature. Okay. So this schematic representation clearly explains how this dipole-dipole interaction is formed. That is Keesom forces. Okay. So this is a polar molecule and this is another polar molecule. When they come closer to each other, these two molecules, they orient in such a way that the positive charge of one molecule is opposite to the negative end of other molecule. So that they attract each other and there forms the dipole-dipole interaction of the Keesom forces. If the polar molecules are oriented like this, then there arises repulsion. That is positive charge, they repel each other. Okay, so this is how the dipole-dipole interaction takes place. Okay, this diagram clearly explains how a dipole-dipole interaction occurs in polar molecules. Okay, so what do you mean by a Debye force? Actually, these are the forces developed due to interaction between a dipole and an induced dipole are called as Debye forces. So, the forces which are developed due to interaction between a dipole and an induced dipole are called as Debye forces. So, let me explain about induced dipole now. Okay, let us consider this as a polar molecule. Like a polar molecule, we have non-polar molecules also. Okay, now let us consider this as a non-polar molecule. Okay, non-polar molecule, and this is a polar molecule. Okay, sometimes this polar molecules distorts the non-polar molecule and induces a dipole moment in it. Okay, this polar molecule, it has a capacity to convert this non-polar molecule into a polar molecule. Okay, so how it happens? See, when this polar molecule approaches the non-polar molecule, the positive end of the polar molecule attracts the mobile electron cloud. So actually, the electrons will be moving around this. Okay, so in a non-polar molecule, the electrons will be moving like this, right? So the positive end of the polar molecule attracts the mobile electron of non-polar molecule and distorts it and changes it into a induced dipole. Okay, so let me explain. Since the polar molecule is distorting the moving electrons of this non-polar molecule, the electrons will be attracted towards the positive end. Okay, so what happens here? See, the moving electrons, it will be attracted towards the positive end of the polar molecule, and thereby what happens? The positive end of the permanent dipole molecule now attracts the displaced electron cloud of the induced dipole. See, both will be held together by an electrostatic force of attraction called as Debye force. Can you understand? So thus the Debye force is formed. Here is another schematic representation. See, this is an isolated oxygen molecule and this is a non-polar molecule. This is a non-polar molecule. See here what is happening. This is a permanent dipole moment, water molecule which is having a permanent dipole. See now this is attracting the electron clouds of the oxygen molecule, that is a non-polar molecule, towards itself, so that automatically an induced dipole is formed here. So what happens? An electrostatic force of attraction is produced between the induced dipole and the permanent dipole. So this induced dipole and the attraction between the dipole and the induced dipole is called as Debye force. Can you understand? Now let us see the next type of force, that is London force, that is which is created due to temporary dipole and induced dipole. Okay, the final one is the London force. London force is nothing but the temporary dipole and an induced dipole interaction. So it's the force developed between instantaneous dipole molecule and an induced dipole molecule. Instantaneous dipole is nothing but a temporary dipole. Okay, so the London force is the electrostatic force of attraction formed between a temporary dipole or an instantaneous dipole molecule with an induced dipole molecule. Okay, I consider hydrogen, oxygen, chlorine, and iodine. Okay, see, actually these are non-polar molecules. Hydrogen, oxygen, chlorine, and iodine. These are non-polar molecules, and monoatomic inert gases like helium, neon, argon, and xenon. All these develop this type of forces, that is London force. Okay, when they are brought together. So according to wave mechanics, the electron cloud is rapidly moving around the nucleus. Okay, see, according to wave mechanics, the electron cloud is rapidly moving around the nucleus. This is nucleus. The electrons are rapidly moving around the nucleus. During this movement, the electron density at a particular point of a molecule may become maximum. Like this, the electrons will be moving towards a particular point and it will become maximum at a particular point. Thus, an instantaneous dipole is created. Okay. Now, the molecule with instantaneous dipole will influence the nearby molecule, thereby causing an induced dipole. Okay. This how an induced dipole is formed? The same way. See, this is a non-polar molecule. Okay. And what will happen? The electron cloud will be moving around this. Okay. And this negative charge will be attracting the positive charge of this non-polar molecule towards itself, so that the positive charge will be coming closer to the negative charge of the instantaneous dipole. So automatically an induced dipole is created. Okay, so this is, I hope you can understand the difference between an instantaneous dipole and an induced dipole. Okay, here there is no forces acting on it. Automatically this non-polar molecule is converted to a dipole. Okay, whereas in the case of induced dipole, this instantaneous dipole is attracting the positive charge of another non-polar molecule and creating a dipole. Now, a force of attraction is developed between the instantaneous dipole molecule and an induced dipole molecule. This is known as a London force. Can you understand? So, if you know the difference between instantaneous dipole or a temporary dipole and an induced dipole, it is easier to understand the London forces. Okay. Of course, this London force is observed in these molecules like hydrogen, oxygen, chlorine, iodine, and also in inert gases. Can you understand? Well, fine students, I hope you might have understood what I have taught today. Let me meet you with another important topic in my next session. Until then, it's Dr. Anita Raj, your chemistry mentor, signing off from you. Thanks for watching.